Covalent network solids consist of atoms held together in large networks, as well as covalent bonds. Covalent bonds is where two atoms share a single valence shell. Since covalent bonds are much stronger than intermolecular forces, this makes the covalent network solids very hard with a very high melting point. Covalent network solids are only made up of nonmetals, and some examples would be diamond, carbon, quartz, and silicon dioxide. On the left is a typical 3D diagram that you would see of a covalent network solid. This particular solid is of graphite. In graphite, each carbon atom is bonded to 3 other carbon atoms in its layer. On the right is a diagram of a covalent bond. As you can see, in the covalent bond, two nonmetals share electrons in its valence shell. The next type of solid we will talk about is ionic. Ionic solids are ions held together by ionic bonds. Ionic bonding is the complete transfer of valence electrons between atoms, and it is typically between a metal and a nonmetal because a metal loses electrons to become a positively charged cation, while the nonmetal accepts the electron to become a negatively charged anion, and this occurs so that both can satisfy the octet rule. Ionic solids are usually hard and brittle and have a high melting point. They are typically to be salts, for example sodium chloride and calcium nitrate. On the left we have a typical ionic bond. Sodium, a metal which has one extra electron, and is going to give it up to chlorine, which is a nonmetal, because it is missing an electron. Therefore, both of the ions can satisfy the octet rule. On the right, we have a 3D model of an ionic solid. The sodium ion is surrounded by 6 chlorine ions because of its coordination number being 6. The coordination number increases as the size of an alkali metal also increases. Next we have metallic solids. Metallic solids are only made up of metal atoms and are usually hexagonal close-packed, cubic close-packed, or body-centered cubic structures. The bonding in metals is too strong to be due to London dispersion forces, and yet there are not enough valence electrons for ordinary covalent bonds between the atoms. The bonding is due to valence electrons that are delocalized throughout the entire solid. Metals vary greatly in the strength of their bonding, as shown by their wide range of physical properties, such as hardness and melting point. In general, the strength of bonding increases as the number of electrons available for bonding increases. Some examples of metallic solids are copper, iron, and aluminum. Here is a visual of a metallic solid. And because of what was said before about the bonding, which is due to valence electrons that are delocalized throughout the entire solid, allows us to visualize the metal as an array of positive ions immersed in a sea of delocalized valence electrons. Lastly, we have the molecular solids. The molecular solids consist of atoms or molecules held together by intermolecular forces. But because these forces are very weak, the properties can vary from low to moderately high melting point and generally are fairly soft. Some examples of molecular solids are argon, methane, sucrose, and dry ice. Here's a visual of a molecular solid. A lot can be told from a molecular solid's three-dimensional visual, such as those with highly symmetrical planar molecules will have a higher melting point than those of lower symmetry, but in contrast, those with lower symmetry will have a higher boiling point than those of a highly symmetrical planar molecule.
But don't look down, 'cause I'm on top of the world.